Hello everyone, welcome to another video of the course. In this video, we will investigate the design and finite element analysis of the case study number 4. So we have a 4 kilowatt benchmark induction motor. Its operating speed is this one, and in the case of the synchronous reluctance motor, this is the synchronous speed. The outer stator diameter is 170, the stack length is 135. This is the terminal voltage, and this is the desired efficiency and power factor we have here. So, for example, during design of this motor, I will use a MATLAB optimization function, okay, to learn how to use MATLAB built-in functions for optimization purposes. Here in this table, also you can see the value of the air gap diameter for the benchmark motor. So, here we have this M file, case study 4, to design this motor. Here in this line, first I generate an instance of the SynRM fluid flux barrier class. The rated output power, I set it equal to 4, the base RPM, number of poles, number of stator slots, number of winding layers equal to 1, the number of flux barrier layers equal to 4. I set the width of the radial rib for the first flux barrier equal to 1, for the second one equal to 0.7, and for the rest equal to 0. Yes, so because the number of flux barrier layers is equal to 4, this is a vector, yes, width of radial ribs, and we should set it like this. We have 4 numbers. The width of tangential rib 0.8, the desired efficiency 83.1, the desired power factor 0.8, the BRY average 1.1, the air gap thickness 0.5, and here I set the value of the magnetic loading, the field factor, and the current density in the stator winding. So, if I place a breakpoint here and run this code, here m.osd is equal to 125. m.lstack is 70. Yes, because I should run the run sizing function here. So let's place a breakpoint, run, m.osd is 198, m.lstack 108. Yes, so if we plot the motor sketch, this is the motor sketch. So as you can see here, the value of the outer stator diameter is 198, but the outer stator diameter should be equal to 170. I want to design a synchronous reluctance motor and replace it with the benchmark induction motor, and I am going to use the same frame. So how I can adjust the outer stator diameter and stack length. So here I used this function adjust OSTL stack. This is the function. We have these inputs, the object, desired value for OSD, desired value for L stack, and here we have the variable names. We specify proper mean values and max values. Because I want to use this MATLAB optimization function fmin_con. This is in optimization toolbox, a good function that we can use for optimization. So let me search it from optimization toolbox. So here you can see different versions that we can set the input arguments. This is the function that we are going to minimize. This is the x0, the initial point for this optimization. A, B, A equal, B equal, lower bound, upper bound, nonlinear condition, and options. So you can use this version, this, or this one. Here is the nonlinear programming solver. We are going to minimize f of x such that we have this constraint. So I am going to use the simple version, just set the lower bound and upper bound of this function. So yes, here first I set the options, the optimization options. You can set the step tolerance, and also you can specify the algorithm for optimization. You can see the properties here. Yes, here you have different options. You can use the interior point, SQP, thrust region, reflective active set, and so on. So we should use this function in this way. First I set the value of the rounding flag equal to false, just to do the optimization in a better way, right? We need to have smooth curves to escape from local minimums. So if I set the rounding flag equal to true, the optimization, right, will be complex. So here just I am going to change the value of the aspect ratio and electric loading and set the value of the outer stator diameter and the stack length, that is 135. So using these arguments, you can add more arguments. For example, you can add the current density of a stator winding, change it from 4 to 8. Yes, so you should have list of variable names, the minimum values, and the maximum values. Here just I want to change the aspect ratio and electric loading. Change the aspect ratio from 0.5 to 2 and electric loading from 20 to 40. So here I set the rounding flag equal to false and set the RGR equal to 5 or 4. to design the rotor first for each iteration. Then I again set the rounding flag true, the rotor geometry resolution equal to 1. Again, I run the sizing function and then plot the sketch. So here in this function, this is the number of decision variables, the var names that we have, and we set the var values. Okay, so then we call this function. This is our error function that we are going to minimize. Yes, so we are going to set the value of the object properties, then run the electromagnetic design core, and this is our objective. We are going to minimize, right, this expression, the absolute value of OST minus desired value of OST plus absolute value of the L stack minus the desired value. Yes, this is the error function, and we have the initial var values and we have the minimum and maximum values. Other options are empty. Okay, so I used this version of the function, the optimization function. Just I set the lower bound and upper bound. So, this is an example. You can extend this idea and use it for other optimization types. Just I want to change the aspect ratio and the electric loading to match these two numbers. So let's run the code. Let me check the error. Trace indexing. Yes, the first input of this function is M. So, yes, the first input is the object, then desired value for OSD, 170, 135, and the rest. So let's run. Here you can see the optimization process. This is the value of the function, and here we terminate the optimization process. As you can see, the value of the OSD, the new values for OSD and LSTAC are 170 and 134.7. The value of the inner stator diameter is 104. The width of stator tooth 4.5. M dot, the value of AC 29. Yes, as you can see, we can match these two values with the constraints that we have here just by using this function adjust OST and L stack. Yes, so you can practice this function. What is the value of the phase resistance? 1.37. You can include the JSW also in this optimization. So here I set it manually. For example, if I increase it to 7.9 and try another example, yes, you can see the new design. What is the value of electric loading is reduced because I increased the value of the current density. The value of the ISD, right? We have increase in the value of inner stator diameter. So you can play with these numbers And even you can run the sensitivity analysis to find the proper design. Anyway, so let me set this value equal to 0.47 and continue with this model. Yes. Anyway, here you can see the value of the width of radial rib for the first flux barrier layer and the second one. Here I didn't consider the radial ribs. The next step is generation of the model in ANSYS Maxwell software. Yes, to perform the finite element calculations, generation of the magnetic loading design, the map curves, and steady state. So what is the desired value of the output torque? Is 25.4. So this design should generate this torque. You can see the numbers that we have here. Number of turns per coil, parallel path, the phase resistance, and other parameters. So let me run the first magnetic loading design. Again, we should apply a mesh constraint, length based. Let's consider 3 and set the number of points on this arc equal to 4. Save the project and generate the mesh. Just I'm going to check the mesh size and the quality of the mesh. Yes, that is good to start the analysis. Here in these regions, because the thickness of the rib is small and we have high saturations, we should consider a fine mesh. You know, we can restrict the mesh size. If I select this edge, for example, yes, we can apply proper mesh constraints. Anyway, let's set the value of theta A from x, that is 55, the current angle equal to 0, and we can run the magnetic loading analysis to plot the flux density, amplitude, and also the flux line plot. Yes. Again, as you can see, in this case, the flux lines are in the direction of the d-axis. The current angle is 0. And set this scale to 1.7. Yes. So in this case, the d flux only we have, the q flux is 0. And let's calculate the static torque curve. Analyze. Just to check the value of the maximum developed reluctance torque. Can this model generate this desired value of the electric torque or not? So simulations are running. We can plot the torque. We should import the output variables. SynRM files, magnetic loading. So yes, the static torque 1, static torque versus the current angle. We can calculate the maximum value. Okay, simulation completed. Here you can see the maximum value of the electric torque, and we can add an X marker, right? Here, as you can see, in this region, the value of the reluctance torque is about the rated one that we need. For example, if I set the value of the current angle equal to 65 and run the magnetic loading analysis, then I can add field markers to check the value of the flux density in different locations of the motor. Here the marker, what is the value of the B here? 1.6, 1.5, 1.6, 1.6. Yes, if we set the value of the current angle equal to this number, and we have this B waveform. What is the average absolute value? 0.48. So the next step is again calculation of the flux linkage curve. So analyze to calculate the flux linkage characteristic. Then we can generate the fraction model and run the steady state simulation to check the value of the power factor and flux linkage curves, the terminal voltage, and so on. Here you can see the radial rips also. We have saturation and this flux line, yes, that we have. So let's plot the flux linkage characteristic. Matrix 1, we have FLD and FLQ in rotor reference frame versus the IS per unit. So yes, this is the D flux when the value of the current angle is 0, and this is the Q flux. So because here I used this mesh size, the simulation time is higher in compared with the previous analysis. So 24,000 mesh elements. Yes. This is the FLQ in rotor reference frame when we set the value of the current angle equal to 90 electric degrees. Okay. We are doing the simulations in parallel. So let's do the steady state simulation for this design. You know, when our assumptions are good, actually we can get a good initial design in ANSYS Maxwell software. I mean our assumptions for the BRY average, magnetic loading, current density, and so on. Here in a steady state model, let's create the fraction model to do this simulation fast. So a steady state one pole. How we can generate the fraction model? First, we should set the value of the theta r 0 equal to negative zero point 0.5 and then generate a relative coordinate system. Yes. For this relative coordinate system, I should set the x-axis 1 millimeter times cosine of negative 5 degrees. The y component of the x-axis is sine. Yes. Again, select all, split again, zx. Yes. We should apply the boundary conditions, independent and dependent boundary condition. Yes, this is the global coordinate system. We have this parameter here, symmetry multiplier. Yes, and let's set the mesh size on these two line objects equal to 0.5. Yes, the motion band reassign. We are ready to do the steady state simulation. One electric period. This is the phase A, B, and C. I set the value of the current angle equal to 65 and run this one electric period analysis. So the aim is to calculate the electric torque profile. Simulation completed. The moving one dot torque. Yes. And let's import the output variables and plot the value of the power factor. Plot the VA, VB, and VC. The value of the flux linkage. Yes, you can see the flux linkage curves and VA, VB, VC. The RMS value is 230. The value of the power factor 0.79. This is the average value of the electric torque, 27. And here, let's set the minimum value. You know, we can sweep over the value of the current angle and calculate the static torque curve. Yes. So let's do this simulation. I want to plot the value of the power factor versus current angle also. So analyze the static torque analysis to run 40 transient simulations and generate interesting graphs. So I want to show the variation of the power factor versus the current angle. Okay, simulations completed. And now we can plot the value of the average value of the electric torque versus the current angle. Yes, this static torque curve, and also we can plot the average value of the power factor. Yes, on the same graph, the RMS value of the phase voltage also, the VA RMS. Yes, let me change the graph, the y-axis, y3. Yes, this is an interesting graph. Yes, the average value of the electric torque versus current angle, the power factor, and the phase voltage. So, as you can see, when we increase the value of the current angle, we have increase in the value of the power factor. Yes, the point that we get the maximum power factor is different from the point that we get the maximum electric torque. So if I add this X marker here, you know, you can see when the value of the phase voltage is 230, we have these values for the power factor, the developed electric torque. In this point, we get the maximum power factor that is zero point 0.8. Yes, but this is the working point, the rated one in our case. Yes, if we set the value of the terminal voltage equal to the rated one. Anyway, when you run the motor, you can set the value of the current angle for different values and calculate the properties of the motor. But as you can see here, the point that we get the maximum power factor is different from the point that we get the maximum reluctance torque. So you can use this M file to generate this model and then do the finite element calculation, static torque, flux linkage, steady state, and also you can run the optimization code, the sequential iterative method optimization fluid flux barrier, and then you can generate the map curves, efficiency map, and so on. So you can do these calculations for practice. Thanks for watching.